Before that, on BBC Radio 4, we take a journey back in time to explore the achievements of a remarkable group of women whose work led to a series of revolutionary discoveries about the stars in the night sky. Sue Nelson presents the Harvard Computers.
At the end of the 19th century, a woman's place was certainly not in the observatory. But an incredible opportunity was about to present itself. A diverse group of college graduates, a maid and a wealthy socialite were hired to work on the astronomical equivalent of the factory floor. They weren't paid to think, but that didn't stop them, because these women went on to make major contributions to our understanding of the stars. They were called the Harvard Computers.
They were brilliant, and they were talented. And when you get a very good mind, it does what it wants to do.
For women to be making scientific discoveries in the heavens, I mean, it really was a big story.
The story begins at Harvard University in Cambridge, Massachusetts. In the 1840s, a state-of-the-art telescope was installed in the College Observatory. It helped to discover a number of stars and one of Saturn's rings, and also pioneered the astronomical use of daguerreotypes, one of the earliest forms of photography. Owen Gingrich, a Harvard professor on the history of science, took me to see it.
This is basically a visual telescope, but the astronomers here were interested in experimenting with newfangled things. And in 1850, it made the first daguerreotype of a star, the bright star Vega. And then they saw that using photography would be a way to get a permanent record of the sky. Not very efficiently done with this telescope, but as the time unfolded and the photography itself was improved, that became the weapon of choice, one might say, for the astronomers.
By capturing the night sky on photographic plates, this brass and mahogany telescope gave Harvard astronomers a new way to study the stars. Alongside it is an equally impressive antique, an original part of another, later telescope that was to play an important role in the lives of the observatory staff.
This is essentially like a huge camera. The lens would be at the other end, 2 feet across, and here's where you put the photographic plates in. And what's interesting is that you can see there are 2 different sizes of plate holders here. There's an inner one, which is good for a 8 by 10 inch glass plate, but then you see the much larger rectangle. That was used for taking some of the giant plates that were used especially for looking for galaxies.
Conditions were right for a great leap forward. Bob Kirshner, Professor of Science at the Harvard Smithsonian Center for Astrophysics.
There was a convergence of a scientific opportunity, the technology, which was better telescopes, but especially photography. And this meant that the rate at which you could take data went way up. Harvard set up a telescope in Peru to observe the southern hemisphere and had stations in the northern hemisphere, was getting data from all these different places on photographic plates. And the photographic plates were kind of piling up because there were hundreds and thousands of them that needed to be inspected and needed to be measured, needed to be analyzed.
The work would require immense attention to detail, and because of the number of plates, plenty of manpower. And this need for manpower became the perfect opportunity for women in science.
I am thoroughly in favor of employing women as measurers in computers. Not only are women available at smaller salaries than are men, but for routine work they have important advantages. Men are more likely to grow impatient after the novelty of the work is worn off, and would be harder to retain for that reason.
This view, expressed by the director of Yale Observatory in 1901, was wholeheartedly shared by his Harvard contemporary, Edward C. Pickering. Astronomy historian Barbara Welfer.
He found out that the men could not work at the price that he wanted to pay. And there was one time when I think he was, or so the story goes, when he was so disgusted with these men, he said, "Well, I'm quite sure that I can get my Scotch maid to do a much better job than you're doing." And that was the beginning of how she came into the observatory and was given many of the assignments and did them so well and so quickly and so beautifully that it gave great encouragement to Pickering of what women could do.
The Scotch maid was Wilhelmina Fleming. Although employed as a domestic, Fleming was an educated woman. She'd worked as a teacher in Scotland before marrying and emigrating to the United States. Abandoned by her husband when pregnant, she joined Pickering's household to support herself, and the observatory director soon realised she had other potential. Fleming wasn't the only woman who worked at the observatory without a background in science, but many later additions were college graduates. All would be computing astronomical data, so Pickering called these women his computers.
The Harvard computers came from a variety of families around in the area. They all lived at home or perhaps in boarding houses at that time. And I think of them as having a privilege to have worked in the observatory as opposed to the women who were up in Lowell and worked as mill girls. They all had good math skills and good writing skills and were dedicated to their work in astronomy. I think there was a connection of working on the stars. It was sort of, working in astronomy was almost like being a little closer to God in those days. And that was a very important piece of it, I think.
Pickering employed 40 women computers during his tenure as observatory director, more than any other university in the United States. Novelist and physicist Alan Lightman.
He was a complicated character. He was gracious and generous. On the one hand, he was compassionate. He was offering these opportunities to women that they wouldn't have had otherwise. But he also was taking advantage of them. In one of his reports to Harvard College from his observatory in the late 1800s, he said that these women were very narrowly trained and very narrowly skilled, and they could really only do one thing. But they were so good at it that he could use them at much lower cost than if he paid men to do the same job. So he was getting cheap labor, and he paid them to work and not to think.
And that work involved examining thousands of images of stars on photographic plates.
Here we are on one of the floors of the plate stacks. We have 3 floors.
Martha Hazen was curator of astronomical photographs at Harvard College Observatory for 33 years. She offered to show me around and led me to a room filled with metal cabinets so I could see some of the photographic glass plates used by the Harvard computers for myself. They're kept inside brown paper sleeves and they resemble row upon row of old 78s.
Here you see, standing vertically, because that's the way plates should be stored, 8 by 10 inch photographic plates, emulsion on glass, in paper envelopes, and there will be 1, 2, 3, 4, 5, 6, 7, 8 shelves, times 4 is 32, so this can hold about 3,200 plates.
And how many plates in total?
We have close to 500,000. I've never counted them. So, but that's what we feel is in here.
All right, I'm looking forward to seeing one.
Right. Well, let me take you over to the desk over here where I've gotten out some things to look at. I'll slide its jacket off here so you can see it.
Oh my goodness, now this is on a light box here, so you can see just a little tiny little black and grey spots.
This is of course a negative, which means the stars are black and the background is clear. And nobody uses these plates without using a magnifier because otherwise you can't see what's on them.
They are minute. What can you tell from this? Just that the larger black stars are brighter than the smaller grey ones?
The brighter the star, the larger the black dot is.
These black dots, by the way, are so fine they resemble a sprinkling of ash on glass. But this wasn't the only type of plate they worked on. Others were produced by splitting the light from each star into its spectrum.
This is a spectrum plate. It was taken by putting a prism in front of the objective of the telescope.
This plate physically looks very different to the other, not just because it's smaller, but whereas the other is a collection of pencil dots. It looks like each pencil tip has been smeared downwards, so it's like a collection of almost just individual paintbrush strokes.
That's right, and if this were in color, the upper end would be sort of yellow, and then it would go through green and blue into violet as you go down.
Now, what could they tell from this plate?
Well, if you look at some of the spectra very carefully, you will find that they are crossed by what in reality are dark lines, but here, since it's a negative, are white lines.
Oh, actually, I just looked at it through the magnifying glass, and you're right, what looks like a single unbroken grey line actually looks, gosh, I'm going cross-eyed looking at this, does look more like a barcode with little white lines across
and
it.
The pattern varies from star to star.
Plate B14674, star 1, class K2, 0 hours 59.7 minutes, plus 4 degrees 15 minutes, magnitude 8.8. Star 2, class F5, 0 hours.
Scientists had already deduced that if you analyse the light from a particular source, then the lines on its spectrum barcode corresponded to the activity of certain elements within it. What they then realised was that by spreading the light out from a star, you could suddenly learn far more about it, purely from the position of its spectral lines. Astronomers discovered that the blue stars in Orion's belt, for instance, showed ionized helium, while the Sun, our nearest star, contained ionized calcium, all from what looks like a smudged pencil point on a photographic plate. When the stars began to reveal themselves, a new scientific adventure began, trying to see if there was some sort of stellar order in the heavens, which is why Pickering needed his computers to examine hundreds of thousands of plates to classify the different types of stars.
At Harvard, the people who were actually doing the classification were the ones who invented this way of sorting the stars by their spectra, and it turns out that that is mostly an effect of the temperature of the stars. So what they were doing was recognizing these patterns, seeing which ones were alike and which ones were different, and then organizing them into groups. And then, as time went by, the physical understanding of what that meant began to appear. And from these hundreds of thousands of spectra came a system of classification and a big catalog, of course, of all those measurements that began to show what stars were. And it turns out stars can't take on just any size or have any temperature. They're very well-defined patterns in the properties of the stars, which were just completely unknown until you had this systematic set of data.
While Pickering was undoubtedly in charge, paying the computers to work and not think, progress was made because the computers not only did the routine stuff, but applied their intelligence as well.
The real scientific work involved something more subtle, like the recognition of patterns. What were those spectra telling us? What kinds of stars were there? What did the spectra mean? And that is something which is not just the laborious, repetitive, tiresome work, but it's based on all of that. So you need both things.
Plus 44 degrees, 36 minutes. Procession 1855, September 17th. These objects were looked up by Miss Mackey on all available spectral plates. A very faint spectrum on plate I23969 confirms a new Class N star.
Wilhelmina Fleming began classifying the stars alphabetically, as Pickering instructed, according to the strength of the hydrogen lines on their spectra. But years later, this system was modified by the computers themselves, when they realised that Pickering's classification didn't quite fit the data. The original A, B, C, D sequence and so on had to be reshuffled to work, and some categories even had to be dropped. The revised order was for 7 star types: O, B, A, F, G, K, M. The hottest blue stars being classed as O and the coolest red stars being M. It's still in use today, although luckily there's an easy way to remember the order by the mnemonic OB, a fine girl, and kiss me. For computers who are considered to have made the greatest contributions were the gifted astronomer Antonia Maury and an astronomy graduate and socialite called Annie Jump Cannon. Cannon's observations formed the basis of a comprehensive star directory called the Henry Draper Catalogue, named after the man whose money set up Pickering's department and helped fund the computer's work.
Annie Jump Cannon measured and recorded the colors of 300,000 stars. It's just staggering to think of how many individual stars that she looked at. And each one you have to look at its light through a prism. And she was able not only to record these colors, but to classify them into various groups called spectral types. And now that is a fundamental basis for understanding the differences between different kinds of stars.
But Alan Lightman is even more impressed by another computer, so much so that he's including her in a forthcoming book on the greatest achievements in science.
The other person, Henrietta Leavitt, made a discovery which I think is even of greater magnitude, and she discovered a means for measuring the distance to stars. Measuring the distance to stars is probably the most important thing that an astronomer can do, and has been an obstacle to astronomy for thousands of years.
Stars are a little tricky because when you go out and look at them, some of them are bright and some of them are dim. But that doesn't tell you whether they're really intrinsically very luminous or intrinsically kind of wimpy stars, because if something's nearby, it can look bright, and if something's far away, it can look dim, even though intrinsically it's putting out a lot more light. So if you have a flashlight and you shine it in your eye, that seems much brighter than the sun. Well, that's not really the right story. The fact is it's just much closer than the sun. So it's very hard to know the real properties of the stars unless you know the distances.
Henrietta Leavitt used the photographic plates to look for a certain type of star. By overlapping 2 plates, taken of the same stars but at different times, she could identify those whose brightness had changed.
A star is sort of a metaphor for steady. But in fact, if you look closely at stars, some of them vary in brightness, and that happens for a lot of different reasons. But one of the most important classes of these variable stars are stars which are literally vibrating. They're getting bigger and smaller. Their temperature is changing over time, and the amount of light that comes out has a nice regular variation. And what Henrietta Leavitt found, very simple thing, is that of these Cepheid variables, the ones that had long periods, that took a long time to get bright and dim, typically tens of days, were intrinsically brighter than the ones that vibrated up and down more quickly. So that was very good and very important, because it meant that there was something you could measure which did not depend on the distance, that is, how long the star took to vibrate. And if you measured that, then you would know whether you were looking at kind of a dim bulb or a bright one. And by measuring the apparent brightness, you could figure out how far away that object is. So this is really good. It was precise, and these stars were extremely bright and, of course, could be seen, as people later found, in more distant systems. And that was the key discovery to showing that the Milky Way galaxy that we live in is not the whole universe. There are other galaxies equivalent to ours. And, of course, that eventually that we live in a universe which is dynamic, which is actually expanding over time. Now, Henrietta Leavitt did not make those discoveries herself, but the work that she did really set the foundation for measuring distances to other systems, galaxies as we'd call them today, and really her work showed a way to measure the distances to these things, which Hubble and others were able to exploit.
Before visiting Harvard, I found just one photograph of the computers. It belonged to Annie Jump Cannon and was taken in 1913. Pickering is standing outside the observatory, surrounded by 13 women, each dressed in long skirts and high-necked blouses, formal and straight-faced.
Well, I think these long-time exposures for photographs wouldn't make you feel very cheerful.
And if anyone should know, it's Dorrit Hoffleit, a 96-year-old professor of astronomy at Yale University. She joined Harvard Observatory as a graduate student in 1928 under Pickering's successor, Harlow Shapley. Hoffleit was assigned as the research assistant to a computer called Henrietta Swope, but, like many of the others, soon began to think for herself. She recalls this period of her life fondly.
Well, after all, we were all extremely proud of working at these institutions.
And what research were you doing?
Well, of course, at first I was doing what I was told to do, namely the variable stars under Henrietta. But then I went back evenings and Sundays and did what I pleased, which turned out to be that I knew there were a lot of photographs in the Harvard collection that had photographs of shooting stars on them. And so I pulled all those out of the stacks, and I thought what I was going to do is determine the light curves for variable stars. I want to determine the light curves of shooting stars. So I had a wonderful time Saturday evenings and Sundays. And so when I wrote a paper, I put it on Shapley's desk. And after a while, I got called up into his office, and he pointed at my paper and he said, "What's this?" His expression was that you cheated on your time. I said, "Well, that's what I came back Sundays and evenings to work on." So he grudgingly accepted that, and he got it published.
You're 96 now.
Yes.
You have an office here at Yale University.
Oh, I thank the Yale so much for letting me keep my office.
What are you working on now? Are you still doing research?
Yeah. I'm also trying to keep up with the Bright Star catalog. I'm working on that, and then I'm writing biographical sketches for a lot of things, which is a lot of fun.
So no thoughts of retiring just yet, then?
Oh, no. I have a poster that says, "I have so much to do that I'll never die," and I'm proving that.
Well, it's good to see you here, I can tell you. Meeting the sharp and extremely likeable Hoffleit, who I swear doesn't look a day over 70, makes you think about all the other women who worked at the Harvard College Observatory. Those who used their intelligence and passion to take advantage of one of the few opportunities open to women in science at that time. Pickering helped these women achieve their dreams. He may not have paid much, but he credited those who made significant contributions in scientific papers, and this helped build their astronomical careers.
Harvard is probably the most famous place for hiring the women, although many observatories did that. But Harvard Observatory got a special reputation because some of the women had their own reputations. They would write the papers and have their names on them. I suppose Professor Pickering looked over them fairly carefully. But often the women were rather reticent about actually presenting the paper at the meeting, and sometimes Professor Pickering or one of the others would actually read the paper, but the women would be present and there to answer questions about the papers, and of course they're always seen in these large group photographs of the Astronomical Society meetings.
I think Annie Jump Cannon was given the most recognition because people knew immediately the value of what she was doing. Henrietta Leavitt's work really was not appreciated. At the time that she discovered the method for determining the intrinsic luminosities of stars, a certain kind of stars, no one appreciated that that could be used to measure their distances, and it was only in the next decade that that appreciation came. But even then, Henrietta Leavitt did not receive any recognition. She received no medals, no awards, no honorary degrees. She just worked mostly in obscurity. There were a few astronomers around the world who later realized the importance of what she had done. She died at age 53, and in 1925, 3 years later, a member of the Swedish Academy of Sciences sent her a letter saying that he was nominating her for a Nobel Prize and didn't realize that she had been dead for 3 years.
And of course the prize can't be awarded posthumously,
No, it cannot.
The work of all the Harvard computers, recognized or not, played an important part in formulating the picture that we now have of our universe. Stars are no longer simply distant objects of wonder. We now know their chemical composition, temperature, size and mass, and even how many millions of miles away they are from the Earth. In some ways, we can almost reach out and touch them.
We are connected to the stars, and it's not just a romantic vision. There's a real physical connection. Stars actually manufacture the chemical elements, changing them from the simple ones like hydrogen and helium into the complicated ones like the carbon that makes up our molecules, the oxygen we're breathing, the iron that's in our blood, the calcium that's in our bones. All those chemical elements were literally made inside stars. So we are stardust. We are star material. Our whole world, everything we see around us, including ourselves, was once inside stars which lived and died before the sun formed.
So if we don't understand the stars, we're failing to understand our own birth and history.
I would say it even the other way around. I would say that part of the fun of it is that by studying the stars, which seems like a cold and kind of technical thing, you're actually finding out about yourself and about the world that we're in. So, in the old days, it was the heavens were the realm of the gods, and that was sort of a mysterious and forbidden thing. And we've changed that into something where we really understand much better through the means that the women here at the observatory were using what the world is and what our place in it is.
The Harvard Computers was written and presented by Sue Nelson. Readings were by Sarah Mennell and Kevin Collins. The producer was Anne McNaught. It was a peer production.